So hello everyone, welcome to our webinar number 10 on uncertainty management in Basin modeling. So today we're going to talk a bit about TemisFlow, our solution for petroleum system modeling, but mostly about CougarFlow, our solution for sensitivity and risk analysis. So before we start, we'd like to thank you all for registering and participating to this event. We hope you'll find it interesting and useful. My name is Marikai. I'll be the moderator of the session, and your main speaker that you can see at the bottom of the window will be Alcide Thébault. So both of us have been working for Beicip for 10 years now. We are both geologists, basin modelers. We have been deeply involved in the development of our software solutions. Here are a few guidelines about the meeting. So as you probably know already, you are automatically muted, which means you cannot speak. So if you have questions during the session, please use the questions tab that is available at right-hand side. We'll have 2 Q&A breaks today, and we'll try to answer them live. If we cannot, though, we'll do it afterwards by email. We might also use the polls tab to ask you some questions from time to time. So if you can check it out, that would be great. And finally, the meeting is recorded. So we will post it on our YouTube channel in a few days. So thank you, everyone. I will let the stage to Alcide now.
Thank you, Marie. And hello, everyone. So this is the agenda for the session. So I will start by an introduction to response-to-phase modeling with CougarFlow, followed by applications to basin modeling for risk and sensitivity analysis. And we will end the session with a quick demonstration of the workflow. After the case studies and after the demonstration, we will have a Q&A break for you to ask your questions and for us, hopefully, to be able to answer them. So let's start by the introduction on response-to-phase modeling with CougarFlow. So first of all, why should we take into account the uncertainties? Well, the answer is that we have uncertainties in our models. So basin modeling is a deterministic approach. So that means that it gives one representation of the reality. And that representation is a simplification of what really occurs, and all the parameters that we input into that modeling are uncertain and can never be sure of what exactly is that value. So it is always interesting to understand what is the variability of our results and what are all the potential models that we may get from our initial approach. So usually, traditionally, to carry that out, people perform multi-realizations with a Monte Carlo sampling, which means that hundreds or even sometimes thousands of simulations are needed to properly understand the variability of the model. The problem is that this workflow can take up to several weeks or sometimes months for a very complex model, which is unaligned with the industry requirements. So in order to avoid that, response-to-phase model-based tools can offer an alternative satisfactory solution, as it is a response-to-phase-based approach, which is built from a limited number of simulations, so from 10 to 100, and that response-to-phase mimics the calculator behavior and allows for a quick risk and sensitivity analysis. So how does that work? So first, we start by defining the objective of our analysis. So we had to understand what is the problematic. So it could be the pressure within a reservoir. It could be the maturity of a source rock. It could be the accumulation in a reservoir. And from that problematic, we define the uncertain parameters that we should consider. So here I will show you an example where we will look at the expelled masses, and therefore the uncertain parameters are the activation energies of the source rock and the initial TOC. So from that definition of the variation of the uncertain parameters, we define an experimental design. So that experimental design are the simulations that are needed in order to understand the behavior of the calculator and build the response-to-phase. So here in this case, we launch 9 simulations, which are all these points here, which give us one total value for the expanded masses for 9 sets of parameters defined as inputs. With these simulations, we first need to check that they are properly calibrated to our known data, so some wild data or some residual TOC in that case, for example. And we interpolate them in order to properly be able to represent the behavior of the calculator within the uncertainty space. So this means that with that response surface, we are now able to estimate what would be the result of the calculator in any location of the space. So for example, right here for that value for activation energy and that value of initial TOC. So that response surface is built through a parametric or a Kriging approach. So usually Kriging, which means that the simulation data is perfectly respected and we interpolate the behavior in between the simulation points. We need to make sure that this response surface is predictive. So that means that it is able to properly estimate what would be the values of the calculator. So for that, we launch a few runs, additional runs that we call confirmation runs, and we check the difference between the response surface and the value given by these simulations. And if we have a good match, that means that the response surface is predictive. If we have discrepancy, that means we should run some additional simulations in order to improve the quality of the response surface. If the quality is good enough, we can run a Monte Carlo sampling on that surface, which just takes a few seconds or a few minutes, and we can run the risk and sensitivity analysis through that Monte Carlo on the response surface. So what workflows can we perform coupling TemisFlow and CougarFlow? So we have actually 3 main workflows, but of course these workflows can be adapted or can be tuned depending on your objectives. But the main 3 workflows are multi-realization, which is that we will launch several simulations in order to understand the variability of the calculator and have various realizations of the model. The second one is the sensitivity analysis, which is in order to determine the contribution of some uncertain parameters on an output property. And the last one is the risk analysis in order to understand the range of possible values for a property, for an output, given some uncertain inputs. So let's look into more detail the sensitivity and the risk analysis. So for example, here a case to illustrate the sensitivity analysis. So if we look at the saturation within this reservoir body, it could be useful to understand if it is the initial TOC from the source rock, or if it is the fault permeability of the migration pathway, so of the fault in that case, which drives the saturation right here within the reservoir. So that will allow us to help with the calibration if we want to calibrate right here, for example, on a known accumulation, or it could also help us understand what elements we should focus on, we should characterize better in order to better characterize the saturation right here. So this is the type of results that we get. So we got that Pareto plot, which gives us, for example, here that the fault permeability is by far the most impactful parameter, and then comes the initial TOC, and the other parameters can be ignored for further analysis. So these are the most influent parameters with their primary effects and their total effects, so which is represented right here. In terms of risk analysis, so this is the main type of analysis to understand to get the P10, P50, P90 of an output. So for example, right here in these turbiditic reservoirs, we want to know what is the range of values that we can get for the saturation and the range of values for the overpressure. So for that, we define a range of variation for our source 1 initial TOC, a range of variation for the source 2 TOC. Then, for example, variation for the permeability of the seal, and a range of variation for the permeability within the reservoir. And depending on all these elements, we get a distribution for the saturation and the overpressure, giving us the best case and the worst case scenario that we can expect. So just to see how we get from that input distribution to that output distribution, this is how that works. So as I mentioned, you define a range of uncertainty for one of your uncertain parameters. This is the result that we should expect from the calculator if you are launching all potential simulations, but we will only launch 4 of them to understand the variability of the calculator. And we interpolate in between these simulations through the response surface approach in order to estimate what would be to mimic what would be the behavior of the calculator. Here you can see that we have a small discrepancy. So this is what I call before the predictivity of the response surface. If that gap is small enough, we can go on with the analysis. So we define the distribution function for the uncertain parameter, and we sample within that, following that distribution. We then project the values onto the response surface, which is almost instantaneous, and that gives us a distribution for the response. So this is how we go from the input distribution to the output distribution. The values, the results that we get are like this one, this kind of graph. So this is for a scalar analysis. So we get the P90, the P50, and the P10. Right here, for example, for the accumulated HC masses. So the minimum would be 2 million. The maximum, the best case scenario that we get would be 2.7 million kilograms within our accumulation, for example. So that analysis can be done at present day. We would get that graph, or through time, and I will show you an example afterwards. So this scalar analysis is ideal to analyze a value within one cell of your model, or within a group of cells where you will take the average or the total value within that group of cells. But actually, if you want to go further than just a scalar analysis, you can now perform an analysis on a pseudo-well. So you can directly analyze all the values throughout the entire sedimentary column. So you would get the P10, P50, P90, for example, right here, are the overpressure along the trajectory of a potential well, for example. And you will get as well the parameter contribution alongside this well. So here, for example, it's the density and the permeability of all the lithologies throughout the sedimentary column, and you know which one is the most impactful throughout your column. So this is a very powerful tool that can assist in well planning. And finally, so this is the development that is ongoing on the 2020 version that we are carrying at the moment with Total, and that will be available through an update of the 2020 version, but it is the analysis on maps. So here you will get directly the P10, P50, P90 of your analysis at the scale of your basin. So you will be able to directly understand the behavior of one unit. So for example, right here, the maturity of the source rock, but it could be all the accumulations within one play, or it could be the pressure fields within one reservoir layer. And that allows for a regional assessment of the risk in one single analysis. So this concludes the introduction parts, and now let's move on to some applications to basin modeling for risk and sensitivity analysis. So the first case will be based on the Iberian margin, which is a model and a reconstruction that was presented in a paper by Manachal, Perron-Penvidic, and Sutra. The whole case is actually presented in one of our previous webinars, which is the thermal modeling with TemisFlow. So I invite you, if you want to know more about that case, I invite you to check it out on our YouTube channel. So here the idea was to actually understand the maturity within all the main depot centers along the margin, depending on the properties of the crust. So here you see that we have a complex crust, hyper-extended, and we wanted to know if it was the reconstruction of that crust or the properties of the different crustal lithologies, like the radiogenic production or the conductivity, that had an impact on the maturity, and what was that impact on the maturity. So this is the reconstruction on which everything was based. So here you see that we have rifting events, which thins, which makes the crust thinner through time, and brings to an uplift of the asthenosphere, warming up the offshore part of the basin. So when we reach the top of our rifting event, we have then a relaxation phase, which comes into serpentinization of the mantle and some areas where the crust has totally disappeared. And then we have a cooling phase, so with a relaxation phase until present day. So here you have the different phases of the crust with their conductivity and radiogenic production. So as I mentioned, these were actually defined as our uncertain parameters. So for example, for the radiogenic production and radiogenic production right here, sorry, and the conductivities, we made them vary by 10% from our reference values. And we made vary as well the asthenosphere depth limits. So we actually made a difference on the maximum uplift. So we said that at the top of the rifting event, either it could go as high as 20 kilometer depths or a bit lower until here 35 kilometer depth right here. So this was the variation for the asthenosphere. Before carrying out the analysis, we checked the calibration of all the simulations that were used to build the response surface. So here we have 12 simulations that we calibrated to heat flow measurements at the surface. So here are all the heat flow measurements. And we made sure that everything was properly calibrated, which is the case here, because we see that the average calibration for all these simulations is always over 87.4%, which is a very nice calibration, which means all the simulations can be taken into account for the analysis and the response surface can be created. So this is the result of the response surface of the sensitivity analysis through a Monte Carlo sampling on the response surface, to be more precise. And so here we see the same result for the 4 depot centers. In every single case, it's the asthenosphere limit, which is by far the most impactful parameter. So we see here that the total effect of the asthenosphere is much stronger than the conductivity and the radiogenic production of the phase sheets. So that means that this is the element that will be critical and we need to characterize at best. And now the result of the risk analysis. So we studied the vitrinite reflectance of the deepest South rock in all the depot centers. So here's the result for depot center A, for example, where here you see the evolution of the vitrinite reflectance through time. So in blue is the P50, in pink is the variation between the P90 and the P10, and here you have the P100 and the P0, so the overall variation. So that variability through time gives us the following values right here. So we see that, for example, in the depot center A, we have at present day a vitrinite reflectance that will probably vary between 159 at the highest and 1.09 at the lowest. So that means we are within the oil window and potentially a little bit within the gas window. So that translates into these values for the entry age within the oil window and the entry age within the gas window. So we see that the entry age within the oil window is not risky at all. So it's around 129 million years in every case. But the entry age within the gas window is way more risky, with a P10 at 120 million years and a P0, which is P90, sorry, which is actually that it never occurred. So these are the results for the other depot centers. We see that we have a very similar trend for the depot center B. For the depot center C, we see that the risk is more important in terms of variability at present day, but at the same time, we see that every single time we obtain, we are within the gas window. So the variability is more important, but we are less risky because we know that every time we will be within the gas window. And that means that the entry age in the gas and the oil window is pretty well understood. And here we know that the preservation of the hydrocarbon will therefore depend on if that expulsion occurred before or after the deposition of the reservoirs. And finally, for the depot center D, right here, we see that we have something that is a lot less risky and actually not as hot because we are further away from the uplift of the asthenosphere, but we are in between the oil and the gas window. So this is it for the Iberian case. So now let's see a second case, which is the Nova Scotian margin, so which is also a margin on the Atlantic Ocean, so on the other side of the Atlantic Ocean. So we will study here the maturity of the source rocks within the D basin, where we have almost no control because at the time of the analysis, we only had 2 wells located on the platform and no real information offshore in terms of maturity. So here we use data that was given by the Nova Scotia Department of Energy. So this is the result of the reference case. So this is the vitrinate reflectance. So where we see that in our reference case, we are mostly within the oil window. This is the transformation ratio of the source rock. Right here, we have the expelled quantities, where we see that in some areas we do not expel, and in others we expel quite a lot. And right here, it is the age when we start the expulsion. And so that was taken as a rule of thumb with the transformation ratio, when the transformation ratio is equal to 5%. So this is when we estimate we will have an expulsion. So we see in some areas the expulsion didn't occur, and in other areas we actually have some expulsion that started as early as 100 million years. So in order to understand the variability and the risk on that model, we made some input parameters vary. So we made the basal heat flow through time vary. So that's the initial value was taken from an extraction between a lithospheric model and the sedimentary model. So we actually used at first a lithospheric model to represent the rifting event occurring during the opening of the Atlantic Ocean. We extracted the heat flow value in order to have a proper lateral variation of the heat flow, and we made that vary by 10% through time. We did the same thing with the surface temperature, which was initially estimated from the paleobathymetry depth, and we made it vary by 20%. We then made vary the TOC of the source rock, which is estimated to be constant throughout the entire source rock layer between 3 and 7%. And finally, we made the type 2 source rock activation energies vary. So here we have the main activation energy between 51 and 57 kilocalorie per mole. So before performing the analysis, we checked that the response surface was predictive. So all the simulations were properly calibrated because we only had 2 calibration points with the 2 wells. So here we made sure that the response surface was predictive. So here are the results in terms of for the vitrinate reluctance, and here for the mass of expelled oil. So we see that the predictivity, which means only using the runs that are constructive that we use to build the response surface, here we see that we have a good predictivity above around 0.8 in 2 cases, but we see, which is even better, that the predictivity with the confirmation runs. So that means that we are able to predict what would be the results in with simulations that are not used at all when we build the response surface. And here we see that we have a predictivity around 0.9 to 1, which is very good overall. So this is good, and it can be used to perform the uncertainty analysis. So these are the results. So for the sensitivity analysis, we can see the influence of the input parameters, which are right here, basal heat flow, activation energies, initial TOC, onto the output parameters right there. So we see that for the vitrinate reflectance, it's almost only driven by the basal heat flow. The other 2 parameters have no impacts, which is actually normal for the vitrinate reflectance. The activation energies and the TOC will not have any impact on the vitrinate reflectance. Here we see that for the transformation ratio, it's mostly the activation energies that have a strong impact and a little bit the transformation ratio. And for the mass of expelled oil, we see that it's actually more or less the same as the transformation ratio. But in the areas where we are very mature, we see that the TOC has actually a stronger impact than the other two parameters. So we see that it kind of varies depending on the kitchen for our different plays. Then in terms of risk, so these are the maps that we can get in terms of P50, P90, P10, P50, P90. So we see that the P90, so which can be considered the worst case scenario, the source rock is entirely within the oil window. So that means we have a source rock that is mature in every single simulation that we ran. And the P10, the best case scenario is that we have a source rock that can be within the gas window or even over mature in some areas. Here at the top, we have the average, which is not exactly the same as the P50, and the standard deviation, which allows us to understand in what part of the basin we have the most variability compared to the average value. So here we can see the same thing in terms of expelled oil, so with the average and the variability, and the results. So the worst case scenario where we see that we actually have in many areas no expulsion at all, because it's not because the source rock is mature that we actually have expelled. It may be still trapped within the source rock. We haven't generated enough hydrocarbons. And here we have the P50, and here the best case scenario with a lot of oil generated. But actually, what is interesting with that is to get the probability maps. So it's another way of understanding these P10, P50, P90, these percentile maps. So here, the idea is to see out of these 10,000 pseudo simulations that we have, how many give us a certain value. So here, this is actually more or less the same as what I said for the V2 net reflectance. We have no simulation that gave a value under 0.6%. So no simulation is not mature. We have most of the simulations which are within the oil window, and in some parts of the basins, we are within the gas window for sure. And in terms of age of expulsion, so this is also very interesting. So 137 and 92 million years are the age of deposits of the main reservoir units. And we see that we almost never expel before 137 million years. We expel a little bit between 92 and 137, and we expel mostly after or more recently than 92 million years, which means that in most cases we expel after the deposition of the reservoir, which is very good for the preservation of the hydrocarbons if that expulsion actually occurred. So this is it for the case studies and for the theoretical part. So before moving to the demo, Marie, maybe we have time for a few questions.
Yes, actually, I see we have one question from Martin. Could you develop the 5% transformation ratio argument for expulsion?
Oh, yes. This is, I would say, a rule of thumb that can be used. I could have also used actually the simulation within TemisFlow gives the moment when the expulsion occurs. So I could have taken that into account. The problem is because we didn't take really well into account in that simulation the adsorption information. So we didn't really know how much was retained or everything. We just used the rule of thumb, which is that when you reach a transformation ratio of 5%, this is typically when the first expulsion occurs. It can be 5, it can be 10. It depends, of course, on the source rock. It depends, of course, on the lithology that you have for your source rock. It's more or less the same rule of thumb when you have when you say that for your transformation ratio at 50%, this is when you have the maximum of expulsion that occurs because you are in the higher slope of your trend. So that was just a rule of thumb to give an overall idea of the age of expulsion.
All right, thank you. We have a second question. For hydrocarbon saturation, we work a lot with energy drive mechanism in reservoir engineering. the changes on the volume of gas and oil or solution gas in the oil is changed depending on pressure. Okay. I'd like to know how the gas and oil window P10 to P90 determination influence on the pressure changes and drive mechanisms.
Well, it will be the exact same thing actually, because the oil and gas that are generated by the source rock have a certain density. So that means the hydrocarbons that you expel early on are mostly oil, so that means they have a high density. The ones that you expel afterwards are gas, so a lower density, which means that your hydrocarbons throughout the system will have a varying density. And within your reservoir, you will first have more oil, then you will have more gas. And we consider the overall density of the hydrocarbon phase, which means that we have a density that varies and that will have an impact on the pressure regime. So of course the scale is slightly different than in reservoir simulations, but it's actually the exact same principle. And now that you mentioned the reservoir simulation, I just want to say on the side notes that here we see that CougarFlow is coupled with TemisFlow, but you could of course couple it with a reservoir simulator, so like PumaFlow, but even with Eclipse or T-Navigator or other calculators if you want to check the uncertainty of your simulations with CougarFlow.
Right, thanks. We have a second question from Martin that actually refers more to Temis and the way we handle hydrocarbon and the type of migration that we use. What is your definition of expulsion? First, free phases, but within the source rock, we have the start of primary migration, or first oil and gas out of the source rock into the overburden carrier, we have the start of secondary migration. So if you can just maybe elaborate a bit more on the expulsion process.
So the one that we are going to take into account is the second one here. So in TemisFlow, if you activate, it's an option that you activate, but if you activate the adsorption option that I mentioned before, and also the organic porosity computation, we will be able to model the primary expulsion, so from the organic matter into the effective pore space of the source rock. But in terms of results, everything is still stored within the source rock layer. And then we will model as well the secondary expulsion, which is out of the source rock into the overburden, either above or below the source rock, because we can have also downward migration, so downward expulsion. And that will be done when we reach the expulsion threshold within the pore space, the effective pore space of the source rock. So, and this one is always taken into account. And this is when we talk about expulsion, we usually refer by default to that secondary expulsion process.
Yes. So just to make it clear, we start generating oil and gas, we start filling the source rock, the effective space available. So either it's just a regular porosity, either you can use the Temis unconventional module with adsorption of components and the organic porosity computation as well. And then using an expulsion threshold based on the rock type of the source rock, we expel hydrocarbon from this source rock layer. All right, I think you can move on and start the demonstration.
Okay, so now let's start the demonstration. So you should see the 2020 version of OpenFlow Suite. So that was just released. So if you are not aware of that, know that it's been just released, and it comes with a nice new feature, which is the analysis along wells. And I forgot to mention before that the analysis along maps is not yet available directly within the software. It's an ongoing project with Total, which aims at developing that option, and that will be released in an update of the 2020 version, hopefully at the end of the year. So here, I will show you actually the analysis along well from a section that I have presented in the presentation, which is the Campos section, so offshore Brazil. So this is the lithology content. So we see here that we have a main, I'm sorry, I don't know why the software, the you have that blinking effect. I think it's from the demo. Sorry. So I will go quickly. So here you have the salt. I don't want to give epilepsy to anyone.
No, but on our side, it's good, Alcide.
Ah, okay. Okay, so it's only on my side. So I will go quickly, not to have an epilepsy seizure then. So then this is the overpressure within the section. So you see that below the salt, we have some overpressure buildup. And with the migration, simulation, we were able to understand where we have the main accumulations. So through one of the major faults, we have an accumulation here in the turbidity traps right here. So these are known fields, but we see that from that accumulation, from that simulation, we also identify right here a potential accumulation below the salt within an overpressured area that could be interesting. So here the idea will be to study the pressure regime. So here with that log pressure analysis trend, we can see the trend. So we can see a small buildup within that shale layer, and then a bigger buildup of pressure underneath the salt. So here, depending on the density, permeability of the different rocks and the hydrocarbons, we want to know what is the range of pressure that we should expect before drilling. So let's define that within CougarFlow. So we can open a new analysis where we will first define, as I mentioned before, the uncertain parameters. So this is what we do right here. So we can, here we see all the input parameters from the simulation. So we can start, for example, with the permeability for the reservoir. So I select the reservoir layer, which is a carbonate layer. Oops, sorry, it went away. Okay, the reservoir layer. And I can consider the permeability for the reservoir, which will be driven by the specific surface of that reservoir, because we use that approach for the permeability. We can do the same thing for the seal. So here in that case, I will take at the same time the permeability for the two seals, so the marl and the shale, which are the two main reservoir layers above the salt that constrain the windows with the salts, and I can add them as a meta parameter, which means that they will vary at the same time. Then I can, so this is the permeability. I can do the same with the density, and I can do the same with the density of the hydrocarbons, for example. So here I can select, for example, the density. So I will take, for example, the density of the water, so which is right here, reference density for the water. Okay, and same thing for the hydrocarbons. So I will take the density of the gas fraction and the density of the oil fraction right here. So HC density. So for the example, that's it right now. I click on finish, and this is here, all the parameters have been added, and here is their range of variation. So here we have the variation, for example, for the specific surface of the reservoir, and I can change the variation if I actually want to make it slightly higher right here. I could do the same for the seal specific surface. I can change also the water density, because here it varies too much, so it's not realistic. So I want the water density to vary between 1000, which is pure water, to 160, which is a dense brine water. And same thing for the hydrocarbons right here. I can make them vary a little bit less to be more representative of the fractions that they represent. So once I have defined a realistic range of variation, I define a law. So here, a uniform law, which means that everything within that uncertainty range is possible. I could change that. And from that variation of the uncertain parameters, I can define my experimental design, which is here a certain number of simulations that are used to constrain the response, to build and constrain the response surface. So here, the software knows that with 4 parameters, usually you need 12 simulations, and I can increase it a little bit to be able to take some of them as confirmation runs. So you see that automatically Here we know the simulations that will be launched and the value that was taken at random for each of these parameters. So now theoretically, after saving all that, you can launch the simulations. Well, I will actually here do it from a workflow that has already been run, where we have all the simulations, and we can see here the results for all the simulations. So for example, the water overpressure in that case, which is right here for that simulation, which is slightly different from the first one. Now, let's actually have, let's define the result of interest. So the part of that result that we want to analyze. So we define a new result of interest, which will be on a tentative well within the offshore area. So it's not going to be a scalar response of interest, but it's going to be a pseudo well response of interest. And I will check directly on the section. So I will select directly on the section the location where I want to perform that analysis. So here I remove the wireframe and I will click so over here, which is where the accumulation was, and automatically it will extract the information over the entire sedimentary column. So this is the location of the well, and these are the parameters that I want to extract. So in that case, the water overpressure, the water pressure, and the mud weight, which is the theoretical density of the mud that I need before drilling. So when that's good, I can save that to compute and to extract the value from each simulation, and then I can move to the analysis. So here it's slightly different. I have one more parameter than what I showed you. So here I actually have 5 parameters with 20 simulations. I can move to the uncertainty analysis parts. Let's start with the sensitivity analysis. So here I will work first on the water pressure. Okay. So here you see the extraction for all the values for that water pressure. So I have all the simulations that were extracted for the water pressure. And here I have the predictivity of the response surface at each depth within each layer of the simulation. And I will just change quickly the response surface definition to take some of the simulations as confirmation runs. So they are not, that means they are not used to build the response surface, and we use them in order to check. Here you see the quality of the response surface. So we have a very good predictivity with the 17 simulations, and we have very good predictivity with the confirmation run. So that means we can predict what would be the value of these runs that are not used to build the response surface. So now I can perform the analysis. So here it's the sensitivity analysis. So we will know what are the parameters that have the most impact on the pressure within the basin. So this is for the first depths, it's only water density. But here I can extract the information for the entire sedimentary column. And what we see is that at shallower depths, it's mostly the water density, which has an impact on the overpressure. Here, when we reach the seal, we see that we have an impact of the seal-specific surface and here of the overburden density, because it's a parameter I took into account as well. And below the salt, which is here at 6 kilometers, we see that the main impact is the hydrocarbon density, which will have the most impact on the overpressure buildup, a little bit the water density, a little bit the seal-specific surface, and even deeper, the overburden density becomes also a bit preponderant. So here we see that with depths, we have a variability of the impact. So let's perform the same thing for the risk analysis. So I select the property that I want to analyze. Here the analysis is already defined for the response surface buildup, and now I will extract I will compute, sorry, the P10, P50, P90 values from the from the results. So this is the results. So from the 10,000 points, I can actually remove here the simulation values to see things better. So I will deselect that, and actually I will display as well the P50 right here. So this is, here you see that with depths, this is the P10, P50, P90 value that we should expect within the basin. So here you see that at 5,000 we have a slight range. Here we go back, so no overpressure when we reach the salts, and then we have an overpressure buildup, which is between here. So we have pressure at P50, which is around 73 megapascal, the highest around 80, and the lowest around right here. Sorry, that point, which is 70 megapascal. So I can do the exact same thing very quickly for the mud weights, just to show you that it also goes quickly. Mud weight, okay. So because here it's a new property, I have to redefine very quickly the response surface definition. So I can select here 3 simulations, which are other simulations taken at random, same thing, and I can perform the analysis in order to know what should be the mud weight that I want to take into that I should consider. So here in the graphic settings, I can do the exact same things, remove the simulations that were used in order to see it better, and here display the P50 curve right here. So this is, in terms of mud weight, the range of mud that I should consider. So if I want to be safe, I can just take the highest value, which is the highest value that I should expect within the basin. So I think this concludes the demonstration, and we can move on to the final Q&A session, Marie, if we want.
Well, no question for now. It was a crystal clear demonstration, I'll see it.
Perfect.
Let's wait 5 seconds to see if someone... Well, no. So that would be the final word. We hope it was clear and not the opposite. And we hope we were able to demonstrate the value of this technology, especially for basin modeling. We hope you enjoyed the presentation and learned new things. So thank you all for attending this meeting. Bye-bye.
Bye.